Okay, this is some information then on the Argand diagram from our ASFurther maths. So just a wee reminder then, every pair of coordinates xy can be plotted on a pair of Cartesian axes. For example, 2, 3 would be 2 across, 3 up, etc. Complex numbers are also distinct. So if you have a pair of Cartesian axes, the x-axis the real axis and the y-axis is the imaginary axis, then for each complex number z equals x plus iy, there is a unique point xy that you can plot using the axis. So the complex number z1 equals 5 plus 3i can be represented then by the point 5, 3. So you can see it here, 5 across and 3 up. In the same way, z2, 4 minus 2i can be represented with 4 minus 2. Each complex number, besides being represented as a point, can also be represented then as a vector. So you can see the straight line, the vector that takes you from 0 to the point 5, 3, and that takes you from 0 to 4, 2. Of course, in this vector representation, any vector of the same magnitude as z1, and z1 could represent z1 the same as z2, etc. The diagram used to represent numbers like this is called the Argand diagram. If the vector method is used to represent complex numbers, then the parallelogram or triangle law for the addition and subtraction of vectors can be used as a representation of z1 plus z2 and z1 minus z2 on the Argand diagram. So if you have z1 plus z2, you do your z1, and then on the end of it you plot a z2, and the vector getting you from the start to the end will be the equivalent then of z1 plus z2. The taken away slightly more complicated, but it's the same sort of format. z1 going this way, z2 going this way. The vector represents z1, take away z2 is going to be from here to here. It's a bit like at vectors, if you remember. How do you get from here to go? You go minus z2 plus z1. Modulus and argument then of a complex number. The modulus of a complex number is defined as the length of the corresponding vector on the Argand diagram. If you go back up here for a wee second, the length of z1 is the distance then from here to here. So it's as simple as that, really. The modulus of z, if the modulus of z equals x plus iy, we write it then as that, and it's then the square root of x squared plus y squared. Just simple Pythagoras then to work out the length of the line. The argument of a complex number is the angle which the vector representing that number makes with the positive x-axis. Positive x-axis here, angle going up. So the argument is just a fancy word for the angle it's acting at away from the positive x-axis. This definition needs a bit of thought though, since as you can see from the diagram, it could be the theta or the phi. Moreover, if theta is measured in degrees, then if you add 360, 720, 1080, etc., then each angle could kind of make it up like that. If it's in radians, then theta plus 2 pi, theta plus 4 pi, theta plus 6 pi, etc., then could be the angle. To get over this problem, we define the principal argument of z as the angle alpha, which the vector makes with the positive x-axis, and such that alpha is between minus pi and pi, if alpha is in radians, or minus 180 and 180 if alpha is in degrees. Let's take a look. It is essential when you're asked to find the argument, sorry you can't even see that, argument of a complex number, that you draw the relevant vector on the Argand diagram, and this way you will know in which quadrant the vector lies, and so you'll be able to obtain the correct principal argument. You should be careful because a calculator will frequently not give the principal argument if z is a complex number when the principal argument is written as argz. Find the modulus and argument of the following. So we're going to draw out a few Argand diagrams here and try and find in the modulus and argument then of each of these. So our first one is 1 plus I, a nice straightforward one. And if you know what you're doing, I would hope you already know the answer here. This is our imaginary axis. This is our real axis, and we're putting the point then 1 across and 1 up. So that would be here. Here's our vector representation, and going like that. Our argument is of course going to be this, and then the length of the line. So modulus is going to be 1 plus I. That's going to be the square root of 1 squared plus 1 squared. It's going to give us then the square root of 2. The argument, that's 1 and that's 1, so we're going to use tan. Tan theta is 1 over 1, and then theta would of course then be pi over 4, or you might then know that then it's 45 degrees. So that's 1 and that's 1. I hope you can see that that's going to be the case then for that. Let's take a look then at part B. Part B is 3 minus 4i. And draw these so we can fit them all in. So 3 minus 4 is going to be like that. This is our imaginary axis going down. This is our real axis. This is going to be our theta. And then that's our 0.3 minus 4. Modulus in this case of 3 minus 4i is going to be the square root of 3 squared plus 4 squared, and that gives us 5. The argument on z tan theta, so we're looking for this angle here, is across 3 and down 4, so it's going to be, sorry, I get the right way around. Yeah, so it's, of course it's opposite over adjacent, so that's going to be 4 over 3, and we get theta then in radians is 0.9273. So the argument of z in this particular case, for measuring, remember, down this way, let's straighten up that z a little bit for us, is going to be minus 0.9273. Next one then, let's go back up to see what it is. At least it's minus 2 minus 3i. So our diagram would look like this. Now we need to think carefully about how we're going to work out our argument here. What I'm going to do is probably work out this angle here. I'm going to call that phi, and then we want it from the positive x-axis, so I'm then going to take that away from pi to get what we're looking for. So let's go modulus first of all. Modulus of 2 minus 3i, there's a mistake there, sorry. 2 squared plus 3 squared. That gives us then the square root of 13, so that's our modulus. Our argument, we're going to work out first of all, this is a tan phi, so there's your opposite, which is 3, and your adjacent, which is 2, so it's going to be 3 over 2, and that gives me 0.9828 whenever I put it into my calculator. The argument then that we want is this angle here. Obviously that's 180 degrees, or in radians that's going to be pi, so if we do this taken away from pi, that should give us then the argument that we need. So the argument of z, so we're calling theta, is pi take away 0.9828. And remember then it's a minus. I've changed it to because we're going down that way then from the positive x-axis. Finally then part 4, they ask us for minus 5 plus 4i. This down so you can see it. Minus 5 plus 4, I'll be doing my diagram then like this. I'd probably work out my phi like that, and then take it away from pi again to get this angle here. So that's minus 5, 4. Of course, this is our imaginary axis, and this is our real axis. So our modulus of minus 5 plus 4i . 41, and the argument then of z, so I'm going to work out tan phi, which is, that's the adjacent, that's the opposite, so it's 4 and a 5 there. and then our argument of z, we work out, we're calling it theta, is pi take away 0.6747, and that gives us 2.467 radians. So that's a couple of wee examples then for our Argand diagram. Let's take a look at one last example, see if we can get our head around that, and maybe that do us. So back up then to the top, express 2 minus I in the form a plus bi, where a and b is a number of the real numbers. Hence, find the modulus of the argument of that and show that 2 minus I 3 plus I and 2 minus I 3 plus I on the Argand diagram. Okay, so the first bit is really kind of more from the earlier videos, so we need to get rid of this fraction here effectively. Hopefully you remember, we need to multiply top and bottom of this and then by 3 minus I. I'll get rid of the imaginary bit then on the bottom. That gives us 6 minus 3i minus 2i, so it's minus 5i, and then that's minus 1. On the bottom we have 9 minus 3i plus 3i, so that disappears of course, and then I squared is minus 1 times the minus 1 then, so it's plus 1. So that gives us 5 minus 5i all over 10, which is a half minus a half I. So that's that written in the correct form. That's our first wee do. Find the modulus and find the argument then of both of those. So the modulus we have been asked for, modulus of 2 minus I 3 plus I is the same then as always as the modulus, because it was the same numbers. That's then going to be the square root of a half squared plus a half squared. A half squared is a quarter, plus a quarter is 2 quarters, which is a half, and then the square root of a half is 1 over root 2. Our argument of what we're asked for, sorry I don't need the straight lines there, is 2 minus I 3 plus I. We're going to have tan theta of a half and a half. That's just 1, so tan of 1 then is just going to be pi over 4. Definitely worth having a wee Argand diagram for this to see where we are with it. So it's of course this number here, which is a half, take away a half I, so it'll be a half across and a half down. What we have just worked out is that is going to be pi over 4. Therefore, our argument 2 minus I 3 plus I is minus pi over 4, because we're going down that way. The final thing they asked for was to show these 3 numbers in on the Argand diagram. We already have one of them in. So let's do the rest of them, and we'll just do a fresh diagram so we can see where we are. Again, I would prefer if you used a ruler here, but I hope we get the idea what's going on. The first one is 2 minus I, so it'll be 2 across and 1 down. It's dreadful drawing, but we're okay. 2 minus 1, real axis. Our imaginary axis. Our next one then is 3, 1. 1, 2, 3, and 1. And then the last one we've already drawn, of course. It's at 45 degrees going this way. And that's a half, sorry, a half minus a half. And those are the things then that we're asked for. Okay.